So let's go ahead and look at buffered solutions. Okay, so what is a buffer? Basically, a buffered solution is a solution that will resist a change in pH when hydroxide or hydronium ions are added. Okay, and basically a buffer is usually going to consist of a weak acid and its salt, or a weak base and its salt. Okay, so an example of a weak acid and its salt would be something like acetic acid and sodium acetate, seen here. Okay, or a weak base and its salt would be nicely represented by ammonia and ammonium chloride. So notice in each of these buffered solutions we have a weak acid or a weak base, and we have a salt that has a common ion. So the presence of both an acid and its conjugate base, or a base and its conjugate acid, are what facilitate the resistance to change when it comes to the addition of hydroxide or hydronium ion. We know that the addition of hydroxide or hydronium ions in solution are going to drastically affect pH. Okay, so basically stopping that process or at least limiting that process is what a buffer actually does. Okay, so which of the following here are buffer systems? Okay, so in this case we have KF and HF. Okay, HF is a weak acid. KF is a salt that has a common ion, which is F minus. Okay, so this is a buffered solution. Okay, KBr and HBr, notice that the KBr is a salt that has a bromide ion. HBr is an acid that has a bromide ion, so they have a common ion. However, notice that HBr is a strong acid. So because this is a strong acid, this is not a buffered system. And we can go ahead and take a look at this third example down here. We have a carbonate ion, and we have its conjugate acid, HCO3, present. The fact that we have a weak base and its conjugate acid in solution basically sets up that buffered system. Okay, so understand we need a weak base or a weak acid, and we need a salt with a common ion in order to establish the fact that we have a buffered solution. In the case of having HBr, which is a strong acid, obviously that's never going to be a buffered situation. And so these are just the basics of what buffered systems actually are. So let's go and look at how this buffering process actually really works. Okay, so consider an equimolar mixture of acetic acid and sodium acetate. Okay, so if I have acetic acid and sodium acetate both present in solution, okay, so I have both of these hanging out. If I add a strong acid to the solution, what's going to happen is that the acetate ion is going to step up and interact with the H plus and subsequently produce more acetic acid. Okay, if I add strong base, on the other hand, the acetic acid is going to step up and react with the hydroxide ion by subsequently transferring a proton and basically give us acetate and water. So basically in this situation, what ends up happening is that the acid and base that are present in solution, the weak acid and weak base that are present in solution, actually interact with, either the H plus, so, if I added HCl or something like that, or the OH minus that's added, so something like KOH or something of that sort. So basically what they do is these buffer components decrease the quantity of H plus in solution and basically make it where there's just smaller pH changes. So, you put a less acidic product in solution instead of, H plus ions, or you put a less basic, product in solution instead of the hydroxide. So basically what ends up happening is you basically temper the pH changes that would be dictated by the addition of a strong acid, okay, or strong base. Okay, so let's go ahead and look at some calculations. If we have 0.5 molar acetic acid and 0.5 molar sodium acetate solution with a Ka of 1.8 times 10 to the negative 5. They want us to calculate the pH of this solution. Okay, so they're not asking us to calculate the pH after addition of hydroxide or H+. At this point, they're just asking us to calculate the pH as the solution stands, which is these two components. So basically, we know we have a weak acid. Okay, from our acetic acid, we know we have a weak base because we have the acetate ion in solution. Okay, and we know that there's going to be no effect from that sodium ion because it's a product of a strong base. So let's go ahead and let's look at how we're going to calculate our pH based on the solution's components. So since they gave us the Ka value, let's look at it from the perspective of the ionization of the acetate ion, or sorry, the acetic acid into the acetate ion NH+. So we're going to write out our reaction like this. We set up our ice table. We know our initial concentrations of both the acetate and acetic acid components. We set up our changes just like we normally would and find our equilibrium constant or concentration values in association with X. Okay, after we've done that, we then set our equilibrium values. We plug them into the appropriate equation. And once we've plugged them into the appropriate equation, if possible, we're going to make our assumptions about our X values. Okay, so if that's the case and that's a possibility, it makes it very easy. Basically, we know that these components will cancel because we'll have 0.5 divided by 0.5. X will therefore be equal to 1.8 times 10 to the negative fifth. Of course, we want to check this value against our original concentration. In this case, it ends up being fine. Okay, after we've calculated that, we then take that hydronium ion concentration and take the negative log of that value. Okay, and that's going to subsequently give us our pH. So the pH of this solution with 0.5 molar acetic acid, 0.5 molar sodium acetate is 4.74. So it's acidic in nature, but not highly acidic. Okay, so another way we can approach the problem or types of problems that we just did before is utilizing what's known as the Henderson-Hasselbalch equation. Okay, and this is the Henderson-Hasselbalch equation right here. Okay, and basically it represents a relationship between pH, pKa, and of course the concentrations of our conjugate base and our acids in the buffered solution at equilibrium. Okay, so we can go through all of the steps that we did earlier, or we can utilize this equation if we know a little bit additional information. Now remember, we have in the examples prior utilized the assumption that the value of X, or the decrease or increase of our acid or our conjugate base, is relatively small. And so we've been dropping the X's out of the equilibrium expression and just subsequently solving for X with that shortcut. Okay, so with the Henderson-Hasselbalch equation, what we're assuming is that the concentration for our conjugate acid and our conjugate base at equilibrium are basically equal to the initial values. Okay, so with that assumption in mind, we can take our initial values and plug them into this equation, assuming that we're dealing with a buffered solution. Okay, so here they're asking us to calculate the pH of a solution with 0.75 molar concentration lactic acid with a Ka of 1.4 times 10 to the negative 4 and a 0.25 molar concentration of sodium lactate. So notice we have lactic acid and we have a salt containing the lactate ion, which is the common link between these two. Lactic acid is a weak acid, so we can utilize this to calculate our pH of our solution. So now obviously we could plug this all into our ice tables and use our Ka value to solve for X and subsequently solve for pH. Or we can use the Henderson-Hasselbalch equation, which is as follows. Okay. Okay, and plug in the appropriate values and subsequently get the same pH. So our pH is going to be equal to the pKa. Remember that our pKa is just the negative log of Ka, so negative log of 1.4 times 10 to the negative fourth plus the log of the concentration of my base, which sodium lactate is going to be that base, 0.25, 0 divided by 0.75, which is the concentration of our acid. Okay, and if we go ahead and plug these into our calculators, we're going to go ahead and get 3.38 as seen here. Okay, so this is just a nice little shortcut The Henderson-Hasselbalch equation allows this calculation to kind of be sped up. People who deal with buffered solutions a lot, like biochemists and biologists, basically this allows them to calculate the pH of their buffered solution straight away without too much work. Okay, in the same vein, obviously, we have another example here. We're being asked to calculate the pH of a solution with 0.25 molar ammonia, okay, with a Kb equal to 1.8 times 10 to the negative fifth, and a 0.40 molar concentration of NH4Cl in that solution. So we have a weak base, and we have a salt that contains the conjugate acid of that weak base. So we subsequently have a buffered solution. Now, in this case, we of course are going to be using the Henderson-Hasselbalch equation. However, in this situation, we're solving this problem for obviously our base. So our Henderson-Hasselbalch equation is going to be represented a little bit differently in this situation. Okay, so our POH is going to be equal to my pKb plus the log of the concentration of my acid. Okay, so in this case, that's the conjugate divided by the concentration of my base. Okay, so we can utilize the same setup that we did last time. So POH is going to be equal to the negative log of Kb, because that's how we get pKb, as we've discussed in previous lectures. Okay, and that's going to be plus the log of our acid. Okay, so our conjugate acid is this NH4 plus ion, so 0.40 molar, okay, divided by 0.25 molar. We go ahead and plug this into our calculator, and that gives us a POH of 4.94. Now notice they've asked us to calculate for pH, so now we're going to use the 14 minus 4.94 in order to get our pH value. So, 14 minus 14.94 is going to give us a pH of 9.05, as we see here. Okay, we could have also approached this problem by converting our Kb to our Ka value and subsequently plugging in our values, our appropriate values, into the regular Henderson-Hasselbalch equation. But I personally feel like this is just an easier approach. So either approach is acceptable. It should have given you the 9.05. You should try it both ways just to make sure that you're still getting the pH equal to 9.05. Okay, so what we need to understand about these buffered solutions is that the Henderson-Hasselbalch equation is based on the assumption that our X values in the equilibrium concentrations are so small that they basically can be ignored. So we're assuming that the concentration of the ionized products, that changeover that occurs, is going to be very small. Okay, so whether you're using the ice table method or you're using the Henderson-Hasselbalch equation, just make sure that you're aware that these are approximation methods that are being used, unless you're using that quadratic equation in the ice table type setup. Okay, so let's go ahead and let's look at how the addition of a strong base or strong acid would affect the pH of the solution that has been buffered. Okay, so if we add 0.0010 moles of solid sodium hydroxide to the previous buffer, how is the pH going to change? Okay, well, we already know that we have the acetic acid, we know that we have the acetate ion, okay, sodium ion and water. Okay, but now what we're doing is we're adding sodium hydroxide. Okay, and we know that in the case of a buffered solution, if there is an acid or a base that can react with whatever's being added, we should subsequently get some sort of reaction. Okay, so in this case, if I add hydroxide, are there any species present that will allow a reaction to occur? Okay, and we know that we have the acetic acid in solution. So acetic acid and and the hydroxide ion from the sodium hydroxide are going to interact and produce water and subsequently more acetate ion. Okay, so hydroxide is going to be a very strong base. Okay, so we know that this reaction process is basically going to occur to 100% completion. So all the hydroxide ion is going to react with as much of the acetate ion as it needs in order to create this water and conjugate base setup. Okay, so we know that this is the case, so let's go ahead and see how this addition changes the concentrations and subsequently changes our pH. Okay, so let's go ahead and let's look at this setup. So before we can set up our ice table and all that stuff, we need to basically look at this from a stoichiometric perspective. Okay, so we know that we are starting with 0.50 molar acetic acid, and we have 0.50 molar sodium acetate in solution. So we know that those are original concentrations of our weak acid and our salt in solution. Okay, we also know that we are adding this many moles of hydroxide. So before any changes have occurred, these are our initial concentrations. Now notice I've broken this down with respect to moles. Okay, I took a liter and multiplied by my 0.50 molar concentration to get my number of moles of acetate and acetic acid respectively. Okay, now we've indicated that the hydroxide is going to react with the acetate basically to 100%. So when we look at our quote-unquote change, our X value, we're looking at the 0.01 moles as being the change factor, right? Okay, so these two are going to interact in a one-to-one way, so after those two have reacted, all of the hydroxide ion is going to get used up, and so the acetate ion is going to decrease, the acetic acid is going to decrease in concentration to 0.49, okay, and obviously we won't have any moles of hydroxide left because it's all going to get used up, and of course our concentration of acetate ion is going to increase because we have subsequently removed a proton from the 0.01 moles of hydroxide and subsequently produced more of that acetate ion. Okay, so now that we have those values or those concentrations after the hydroxide has used the acetic acid, we now have our initial values for our ice table. Okay, and assuming 1 liter, okay, I'm just going to divide out by 1 liter and subsequently have our new concentration values. Okay, so I plug these into the ice table, I look at my change in X, I subsequently have my new equilibrium values. I'm going to set those equilibrium concentrations into the equilibrium expression for the ionization of this acid. And of course I'm going to make the assumptions that I have in the past. Okay, I'm going to assume that the x's are very small with respect to the overall change. And that's going to simplify my calculation, and I'm subsequently going to find that x is equal to 1.7 times 10 to the negative 5. We know that x is equal to the concentration of H+. So if I want to know the concentration, or excuse me, the pH of that solution, I'm going to take the negative log of my H+ that I just calculated, okay, and I'm going to subsequently plug that in and find that I have a pH of 4.76. Okay, so our change in pH, we know that the original pH of the buffer solution alone was 4.74. Okay, and the new pH after we've added some of that hydroxide ion is now 4.76. So we have seen an increase in pH as we would expect when you add a base, but the change is extremely small. So basically this buffer solution of acetic acid and sodium acetate has done a good job to temper the change that would normally be caused by the addition of that hydroxide ion. Okay, so in that same process, maybe we should compare what the concentration, or excuse me, the pH of a solution would be if I just added sodium hydroxide to a liter of water. Okay, so basically if I take the concentration of, or calculate the concentration of hydroxide in solution, sodium hydroxide is going to give me a hydroxide ion concentration of 0.01 moles divided by 1 liter, which gives me 0.01 molar. Okay, I can utilize the Kw expression to subsequently calculate my H+ concentration. Okay, so the 1.0 times 10 to the negative 14th divided by 0.01. Okay, and that subsequently gives me the concentration of H+, which is 1.0 times 10 to the negative 12. If I take the negative log of that, that's going to give me a pH of 12. Okay, so if I just had plain old water and I added the same amount of sodium hydroxide to that water solution, my pH of that solution would be 12. Okay, obviously that's a huge change from the normal pH of water, which is 7. So When the buffer is not present and you add a strong base or you add a strong acid, you're going to see a very, very large change in your pH value with respect to the original pH of that solution. Okay, so the buffered solutions, guys, they resist the change in pH and subsequently allow the pH of that solution to remain relatively unchanged based on the properties associated with the acid and conjugate base present. Okay, so some more quick facts on buffers. If you have equimolar concentrations of any weak acid and its conjugate base, or weak base and its conjugate acid, that's going to give you a pH equal to the pKa of the weak acid or the pKb of the weak base, depending on how you're doing your calculation. Okay, because obviously taking the log of 1, as you would in the Henderson-Hasselbalch equation, allows that relationship to be seen, right? So plus the log of your acid or your base over your acid concentration. If these are equimolar, if they're 1 to 1, then when you calculate the log, it's going to be equal to 0. So pH and pKa will be equal in that situation. As I said, pOH and pKb can be equal as well, depending on which version of the Henderson-Hasselbalch equation you're using. So just as a summary real quick of buffered solutions, buffered solutions have relatively large concentrations of weak acid and corresponding conjugate bases or weak bases. And basically these weak acid, weak base combinations are what actually facilitate the removal of H plus or OH minus from the solution. Okay, when we add H plus to solution, we know that the weak base or that conjugate base that's present is going to interact with it and subsequently produce a product that's not as acidic. In that same way, if you add hydroxide ion, the weak acid that's present is going to step up and interact with the strong hydroxide base and subsequently produce a less basic component that subsequently allows you to really overcome the large changes that would normally occur in just a pure water situation. Okay, so buffer capacity is referring to the extent to which a buffer solution is going to actually prevent a large change in pH upon the addition of a strong acid or a strong base. So buffer capacity is going to depend on your pH and your concentration. So the pH, basically the closer your buffer solution's pH to the weak acid's pKa, the greater that buffer capacity is going to be. So when your pH and your pKa of the buffered solution and the acid are close, the buffer capacity is greater. Concentration, basically the greater the concentration of the weak acid and its conjugate base, the greater the buffer capacity, right? Because obviously the more of that weak acid or weak base you have in solution, the more H plus or hydroxide ion you could add before a large pH change would occur. Okay, so remember that the closer your pH is to your pKa of your weak acid, basically the better a buffering situation you're going to have, or buffering capacity you're going to have. So we've been given several acids here, and we've been given the corresponding Ka values. Okay, if we go ahead and take each of these Ka values and go ahead and convert them into pKa values, we get a pKa here of 2.86. We get a pKa here of 4.88. Okay, we get a pKa here of 4.19. And we get a pKa here of 7.45. Okay, so remember that our buffering capacity is going to be maximized when our pH and our pKa values are as close as possible. Okay, so if we look at the pH equaling 4.30, okay, that makes benzoic acid the closest with respect to our pKa. So the reality of that is that the relationship between the amount of benzoic acid and its conjugate base is going to be the closest to 1 in this situation. So the best choice for this type of solution is going to be to utilize benzoic acid and its conjugates.